closure properties of regular languages. Context-free languages are closed under so the following properties. First one, union. So consider an example of grammar language L1 is equal to a power n b power n such that n greater than 0. It's one grammar. And the second one, L2 equal to p power m on b power m where n greater than or equal to 0 such that union of L1 and L2 will become a power n b power n union c power m d power m. So this will also become the context-free grammar. So L1 is a context-free grammar, L2 is a context-free grammar, L1 union L2 will also become the context-free grammar. So now the context-free languages are closed under union operation. In the same manner, concatenation also. If L1 is one language, L2 is another language. So then concatenation of L1 and L2 will also become context-free language. Clean star is also. If L1 is a context-free language, then L star is also L1 star is also a context-free language. The same thing with intersection. For example, intersection regular if L1 is a regular language and L2 is a context-free language, then L1 intersection L2 is a context-free language. And context-free languages are not closed under intersection. L1 and L2 are the context-free languages, then L1 intersection L2 is not necessarily a context-free language, so which are not closed under intersection and may not be context-free language in the terms of operation complement also. If L1 is a context-free language, then L1 may not be a context-free language, complement of L1. So decision problems of regular expressions. Decision problems are the problems which can be answered either yes or no. There will be some decision problems, yes or no. It can be done yes, it can be done no. Oh, like this. Finite automatas are one type of finite state machines which contain a finite number of memory elements. So we can memorize only finite amount of information, that we know that one. So here we have finite length of tape. So we can remember only some length of the information only, finite amount of information only. So FA can answer to these decision problems which requires only a finite amount of memory. So those problems are whether a string belongs to the regular expression or not. So it requires limited memory. We can just say yes or no by using FA. Whether the language set of of an FA is on finite automata, mission M is empty. Whether the language set of in a finite automata is finite or not. Whether there existing any string accepted by two finite automatas M1 and M2 or not. Such type of examples are considered decision problems related to regular expressions. So now we will see some of the examples of previously asked these questions. If L is a language over sigma is equal to a comma b, which one of the following languages is not regular? The first option is suffix of L equal to y belongs to sigma star such that xy belongs to language. So this is one option. The second one is w power to the r such that w belongs to some language L. Another option, prefix of L is equal to x belongs to sigma star such that their existence y which belongs to sigma star such that xy belongs to language. And also the next one, L dot L to the power of 4 that is equal to xy such that x belongs to L, comma y to the power of 4 belongs to language. So in this one, which languages is not regular in the sign? W to the power of 4 such that W does belongs to language because the finite automata will have limited memory. It cannot remember the length of information. So here we have to remember string, the reverse of the string also. So there is no lengthy memory capacity in that one. So it's not a regular language. And one more the thing, language L1 is defined by the grammar. S1 tends to A, S1B or epsilon, that is one given grammar defined by language L1. And the next language L2, which is defined by the grammar, S2 tends to AB followed by S2 such that or epsilon. So these are the productions for the grammar defined by the language too. So considering the above following statements, P tends to L1 is a regular language, Q L2 is a regular language. So these are the two statements given P and Q. So in these two statements, which statement is true or which statement is false or whatever all the true, we have to identify. So L1 defined by the grammar. S1 tends to A, S1, B. What happens? We can replace S1 again with S1. In the sense, A, S1, B again we can replace. Now it will become A, S1, B, B. Again we can replace with S1. So triple A, S1, triple B. In place of S1 we can replace with this epsilon also. So now the string will become triple A, triple B. A, it will become the language A power n, B power n. But such type of languages will not remembered by the regular languages. So L1 is not a regular. So P is not a true. P is a false. And coming to the second language, S2 tends to AB, S2. So again we can give AB followed by AB. Again AB followed by AB. So one number followed by the other number continuously we can remember through using the regular language. So L2 is a regular language. So here we can conclude that P is a false statement and Q is a true statement. And they had given one regular expression. For that regular expression, we need to give the minimized size of DFA. The expression is 0 plus 1 whole star followed by 0 plus 1 followed by 0 plus 1 whole star. Now, how we can draw here a FA for this one? Lakshmi Suman. Ah, link. So it is Q state. It is one state Q1 and it is another state Q2. So it is initial state. So it is initial state and it is final state. So it's a final state. It's a final state. So here the expression is 0 plus 1 whole star, 0 plus 1, 0 plus 1 whole star. 0 plus 1 whole star, 0 plus 1. ఏమో సార్ నేను నంబర్ అడిగితే పోలేదా సార్? సార్ ఆ అబ్బాయి ఎప్పటి నుంచి వస్తున్నాడంట? కాదు, థర్డ్ ఫేజ్ కన్నా ముందే వస్తున్నాడంట. ఒకసారి మధు సార్ నంబర్స్ ఉన్నాయి చూడండి. So it is Q1 tends to Q2. So 0 or 1 whole star in the sense here itself we can write 0 or 1 as a self loop and 0 or 1, so that here we can write here we can write 0 comma 1 and here also 0 comma 1. So minimum number of states required is 2 here. So the answer for this one will be the 2. So the minimum number of states required. So in the same manner, it's a regular expression question. Already we discussed now. Set of all binary strings having two consecutive zeros and two consecutive ones. They should be two consecutive zeros and two consecutive ones. For that one, we need to write regular expression by checking all the constraints. So you check that one. In the same manner, let L be the language represented by the regular expression sigma star equal to 0, 0, 1, 1. Sigma star where sigma equal to 0, comma 1. What is the minimum number of states in a DFA that recognizes L complement? So L complement ki required one we have to check. So that is 5. Same here also, the length of the shortest string not in the language over sigma equal to a comma b of the following regular expression is shortest string not in the language. So here all will be the epsilon. So minimum string will be the epsilon, and then we can have a followed by b and ba. We can have b followed by ba or a. We can have 3 and 3 answer is And consider the finite automata in the following figure. What is the set of reachable states for the input string 0011? To reach 0011, we have at q naught, so we'll take q naught 0, again 0, 1, 1, 0, 0, 1, 1, q naught, q1, q2. So up to Q2 we can reach here. By taking 0, we will be stay in the Q0 itself, and by again taking 0, Q0 will stay in the same state, and if it reaches 1, it is moving to the Q1 state. And here if it is reading 1, Q1 by reading the 1, it is moving to the Q2 state. So up to Q2 we can reach by reading this string. So Q0, Q1, Q2. And the next one, L1 equal to a power n such that n greater than or equal to 0, and L2 equal to b power n such that n greater than or equal to 0. Consider L1 dot L2 is a regular language. L1 dot L2 is no equal to a power n, b power n. Which of the following is correct? So the first one is L1 dot L2 is a regular language. A power n, a followed by b we can take. But a power n, b power n we cannot take. Consider the languages L1 equal to pi, L2 equal to a. Which one of the following represents L1 followed by L2 star union L1 star? L1 followed by L2 star. Pi followed by a star. So it will become I. Which one of the following represents union pi star? So epsilon. Next one, what is the complement of the language accepted by the NFA shown below? Assume that sigma equal to A and epsilon is the empty string. Here by taking single A, it is reaching final state. Again by taking 2A's, 3A's, 4A's. By taking nothing, it is not reaching the final state. So it won't be epsilon. It should be A epsilon. Complement of the string. So actually by taking A star we are reaching. By taking single A. So we cannot take A star in the sense epsilon is also present. We have to write the complement of the language. Epsilon A and so on. So complement that one without taking anything it is not moving to the another space. So epsilon is not present in the given language. So that is the complement of the given language. Which of the following languages over the alphabet sigma is equal to 0, 1 is described by the regular expression 0 plus 1 whole star followed by 0, 0 plus 1 whole star followed by 0, 0 plus 1 whole star. The set of all the strings containing the substring 0, 0. The set of all the strings containing at most two zeros. The set of all the strings containing at least two zeros. The set of all the strings that is being end with 0 or. Here at least with 0, 0 containing of two zeros at least as a minimum string, we can get more number of strings. So the set of all the strings containing at least two zeros will be the answer for this one. And consider the set of sigma star. Consider the set sigma star of all the strings over the alphabet. Sigma is equal to 0, 1. Sigma star with the concatenation operator for strings. So does not form a group. This does not form a group. The regular expression 0 star followed by 1 0 whole star power to the whole star denotes the same set as. So this none of the above will follow the same rule. Given an arbitrary non-deterministic finite automata NFA with n states, the maximum number of states in an equivalent minimized DFA is at least 2 to the power of n states should be presented at least to make a minimum equivalent with the DFA. Consider the following two statements. 0 to the power of 2 power n such that n greater than or equal to 1 is a regular language. And the next statement 0 power m 1 to the power of n 0 to the power of n plus n such that n greater than or equal to 1 and n greater than or equal to 1 is a regular. Which of the following statements are correct? Only statement 1 is correct. 0 to the power of 2 power n is a regular language, but 0 power m followed by 1 power n followed by 0 power m is not a regular language. We cannot remember. And the next one, let L denotes the language generated by the grammar. X tends to 0 as 0 or 0 0. Which of the following is true? At least by two zeros. It's a context free but not regular. So it's a context free but not a regular language. 0 0 can be replaced again with 0 0, again replaced with 0 0 and so on. So number of zeros. Consider the regular expression 0 plus 1, 0 plus 1 and so on n times. The minimum state finite automata that recognize the language represented by this regular expression contains 0 or 1, 0 or 1, 0 or 1 up to final state. So n plus 1 state should be there. N plus 2 states will be there. It's a NFA, so finally 0 1 should be attached with some other state. So n plus 1, n plus 2 required. How many substrings of different lengths can be formed from a character string of length n? Substrings of different lengths n into n plus 1 by 2. The string 1101 does not belong to the set represented by 1101. Both can be. So consider the grammar L1 union L2 is a regular, then both L1 and L2 must be regular. The class of regular language is closed under infinite union. Two are false. Neither one nor two. Both are not true statements. Which of the following regular expression represents the set of all binary strings with an odd number of ones? There should be an odd number of ones. Zero star 101 power 1 followed by 0 star, 1 followed by 0 star, whole power star, 1 followed by 0 star. So these are on the finite automata and regular language. Question and answer previously sessions. Now we'll see the on the pushdown automata and context-free languages. Consider the language a power n such that n greater than or equal to 0, union a power n, b power n, n greater than or equal to 0. L is the deterministic context tree, L2 is the context tree but not deterministic context tree. L is not a L of k for any k. So L is a deterministic context tree language, and then L is not LL of k for any k. So which won't be the true for any k value. Which of the following languages generated by the given grammar? S tends to AS or BS or epsilon. So AS, AS, BS, BS. AB whole power star. So the lexical analysis for a modern computer language such as Java needs the power of each one of the following mentioned model in necessary and sufficient terms. Finite automatas, deterministic Turing machines, pushdown automatas, non-deterministic Turing machines. Finite automata. In lexical analysis, by using finite automata, we will perform the will perform the will divide into the tokens of the given string.